Please remember that what we have done so far is without considering the early effect. Now let's consider it. So what we have already achieved for AC operation, for a small signal AC operation, transistor is replaced by looking into the base with these schematics, one of these, right? Voltage controlled current source, current controlled current source, right? Which current, which voltage? Base to emitter voltage, base to emitter current. So that's why we have a resistance at the base side, right? Or we have the transistor working for a small signal amplification by looking into the emitter with this circuit, this one or this one, right? So this is shown as the voltage controlled current source, and this is shown with the current controlled current source, right? Would be the same, right? Because these voltage and currents are interrelated with this resistance, right? And because you are looking into the emitter, so you want to actually relate this output current, because this is the output port at the moment, right? This output current source with the parameters of your desired terminal, which is emitter. You are looking into the emitter, right? So looking into the emitter, the voltage, the current, you are having a resistance at the emitter, right? We already have discussed in detail the resemblance between these two models, right? So pi model, hybrid pi model can have two forms. You can write the output current source either by a voltage control relation or by a current control relation. Otherwise, everything is same, right? Same is the case for these key models, right? So far we have replaced our transistor working with small AC signals with either hybrid pi model or T model, but we have not yet considered the early effect. So what if the output resistance of the control source exists? It will exist if we consider early effect. So this is why this current source, if it is a source, then it would be an ideal source because it does not have a resistor, right? So recall the early effect, how you have modeled, right? You saw that you have a not a constant current when you make your collector base junction reverse biased. It also depends on the collector to emitter voltage, right? And you actually use the effect of these curves as if they are extended to the negative side, and actually they actually meet at a point minus VA, right? And we use this point and obviously the Q point which we already derived or biased. So we can use our bias point and we can use the transistor property of early effect, and we can have a resistance, output resistance, if we would have considered the early effect in our collector current relation, right? Remember, we for large signal models we also said that large signal model is biased with diode at the base to emitter side and current source at the collector to emitter side, and current source relation this one, right? So there is nothing much difference with this large signal model and our this time considering uh, parameters of the small signal model, right? So this one is basically for small VBE, this becomes linear. We already have this diode is nothing but modeled as a resistor because of forward bias. base to emitter junction, right? So without early effect, we does not have this one also previously, right? So this time also we can put it here, right? If we would have considered the early effect while we were discussing the total voltage of base to emitter, the AC part of the base to emitter voltage along with the DC biased part, and then we have used the equation without early effect. If we would have used the equation with early effect, we would actually obtain this one. So it's not too late, right? So we can consider it now without solving by just using our previous knowledge, right? So it is actually out of your syllabus as well. So that's why we are not going to drive that relation again with early effect. So you just take this effect from the knowledge of your large signal model, right? So now we have hybrid pi model. If we are looking into the base for a transistor, BJT transistor working for an amplifier application for small signals, we can replace it with hybrid pi models of these kinds. Both are same. One, the current source is related with the base current. One current source is related, just this equation base. You can write both the things at the same time. It's okay, right? Or if you want to model it by looking into the ammeter, you would be having these schematic models, right? So again, you have a new thing R naught here in between collector and emitter, right? So without early effect, only this one. With early effect, this one. That's why you are actually considering the collector to emitter voltage as well, right? So this ends up with your final model, hybrid pi model or T model, right? So controlled current source is behaving as a practical source now, right? Because every practical source has its output resistance, right? So a current source would be having a output resistance parallel to that current source, right? And then you can put a load here, right? And a voltage source has a series resistance. For example, if this is a voltage source not designed by you, but you are using it, right? So your load is this one, right? So it means if this source is not ideal, it would also have a series resistance here, right? Got it? But at this time, I am also considering this source to be an ideal source, right? At least for this instance, so that I can clarify the new things instead of introducing again and again new and new and new things, right? So just take this source an ideal source as well. Later you will actually see if you want to, because obviously if you made a transistor, you made an amplifier, user has to has to apply some input voltage with some source, and that source is practical source, right? So currently ideal source, but this is practical, right? Now practical models, right? So nothing special. You actually have a relation of R pi, you have a relation of RE, whatever model you want to use, you have a relation of GM, right? Three parameters for small signal modeling, and another one as R naught. We just need again your biasing point. It's about your biasing point. So it means collector to emitter dependence on IC. Obviously, we already know that, just we are repeating, is depending on your Q point, where your Q point is, right? And obviously the your early effect, which is the common for all the curves, right? So it depends on this one. So how much current is from the value divided by this one is this one, where your Q point is. So this one is the delta change. So you are here now, right? So it will be depending on your Q point, where your Q point is. So if your Q point is here, you are actually this much away. So you have to add this factor. and which is depending on this one and the early effect, right? So now how to apply these models for solving some circuits? Small signal model allows you to represent effectively the AC equivalent circuit, right? And then to relate different parameters of the circuit for AC signals, right? The process of AC signal analysis actually want you to surpass all these steps. Don't panic. We have already done most of the steps, right? Because first one is eliminate the signal source, the AC signal source, and determine the actually find the DC equivalent circuit and then determine the DC operating point and load line and something, right? VCE, ICQ, VCEQ, right? And then calculate the values of the small signal model parameters. GM, we already related it, IC upon VT, R pi, VT upon IB, or RE, depending on which model you are using. Pi model, T model. RE is equal to VT upon IE and R naught, the early effect. VA plus VCEQ divided by what? VA, right? And then eliminate the DC sources because we have found the DC parameters. We have found the AC parameters, which basically depends on the DCQ point parameters, right? Now we are going ahead to have an AC equivalent circuit. So you have to remove the DC sources. DC voltage source should be short circuited and DC current source should be open circuited, right? And then replace the BJT. Then you will get the AC equivalent circuit, right? And then replace the BJT with the small signal model of your choice. Although any one of the models, pi model or T model can be used, but one might be more convenient than the others for the particular circuit being analyzed, right? So this point will be made clearer later with examples, right? And then you can analyze the resulting circuit to determine the required quantities, for example, input resistance, output resistance, voltage gain, and so on. The question we actually left open for in our last lecture, basically last end of last video, right? So most of the steps we already did, right? We have to do only this thing as new one, right? So let's take an example, right? So the process will be illustrated by pursuing the same example that we have used for DC for common emitter amplifier design, right? So we have designed this amplifier, common emitter amplifier, but without emitter resistance and tested it for AC, right? Please recall this thing from our previous lectures, right? So at this time, we are actually going to analyze this, that somebody have already designed it. You are going to analyze this circuit, right? And basically you have these questions. For the given amplifier, this is the given amplifier. Draw the DC load line, find the Q point of the amplifier and locate it on the DC load line. Draw the AC equivalent circuit and provide its parameters by taking these values, these constant values. Write the expression of voltage gain. Calculate the numerical value of the voltage gain, which you express numerically here, right?